Normally we know that the heavier something is, the higher the melting or the boiling point would be, because it takes more energy to make it melt or boil if it's heavier. They're all the same size though. They all have the same number of carbons, the same number of hydrogens. So we can't use that as a factor. So we need to think about intermolecular forces in dealing with these. And let's look at how they're drawn out. So we're going to get much more into this when we talk about organic chemistry. For the time being, we'll see, oops, that is not where I wanted that, go back. Okay, CH3 is starting us off here. So I start out with a carbon that's bonded to 3 hydrogens. And then it says that that is bonded to a CH2, carbon with 2 hydrogens on it, followed by another CH2, carbon with 2 hydrogens on it, followed by another CH2, and another CH2, and then we're ending the whole thing with a CH3. So that's a very nice linear one. Our next one is very similar, but not quite the same. We know that it has the same number of carbons, same number of hydrogens, but, and we start out the same way, let's see, CH3, so C with 3 hydrogens, bless you, attached to it, and then we have a CH, and attached to that CH is a CH3. So I have my CH, and attached to that CH3. Then I have another CH2 like I had in the last one, so C with 2 hydrogens, another CH2, C with 2 hydrogens, and finally a CH3 to end it all. The next one is very similar, except that the offshoot of CH3 that I have is on the 3rd carbon. It's on this one. So I have a CH and a CH3. Oops. My last one, let's see, use orange on this one. I have a CH3 followed by a carbon that's attached to 2 of the CH3 groups. So that's right here. My carbon has a CH3 and another CH3 coming off of it, all off of the main line. So each of these have a main line. That's the backbone of my carbon chain. And we see the nice straightest chain is the first one. The least straight chain with 2 offshoots on it is the 4th one. And the other 2 are both kind of equally odd. Well, I pulled out some Legos because I think that these Legos help us understand what's going on here a little bit when we talk about van der Waals forces. Van der Waals forces are between either noble gases or between nonpolar molecules. All of these are nonpolar molecules. There's no big electronegativity differences, and what little electronegativity differences there are, they're canceling each other out as we go. So it's nonpolar. So we can think of which one would have the most van der Waals forces. And we can't tell based off of the mass. What we can say is that, let's say this is number 1. But let's say that these are my carbons going across each set of 2 can be a carbon. And so I've got 4 carbons on this one. This one, I also have 4 carbons, but I have an offshoot of 1. So I've got the same number of carbons, but they're differently shaped. And I want to come in with different molecules and see if they'll interact. So if I take my second one, I could come in from the top, and there's one place for my interactions to occur. Or I could go from the bottom, and I'd have 3 places for interactions to occur. Either way, that's not a whole lot of ways for it to interact, compared to my first one, where I have 4 carbons in a row. I have another one of the same molecule coming in, it has 4 places that it can interact quite nicely. So we've got more places for it to interact, so we're going to have it have more van der Waals forces than I would on this one. More van der Waals forces means that it's harder to break apart. The harder it is to break apart, the higher